Hi, my name is Leen, and in this video I would like to talk about the Dataflash Peripheral, found on all versions of Renesas' newest microcontroller family, the RA. All microcontrollers require some form of memory to be able to function efficiently. Typically, they use RAM or random access memory to store volatile data such as variables, ROM or read-only memory to store firmware, but this is nowadays nearly always flash that can be programmed in circuit. And often they also need some form of non-volatile memory to store small amounts of variable data, for instance calibration data. Traditionally this was an external EEPROM or electrically erasable programmable memory IC that was accessible via I2C or SPI. In the case of the RA, this is replaced by an internal version called Dataflash. Here we see the memory map of the RA2E1 taken from the user manual as an example. This microcontroller supports a 4 GB linear address space ranging from 0 to FFFF that can contain both program and data. The memory map is built up with several designated spaces for different types of memory, as well as specific locations for registers that control the operation of the microcontroller. The flash block is dependent on the size of the flash in the particular version of the microcontroller. In the case of the RA2E1, this can be either 32, 64 or 128 kilobytes. The flash can be programmed in 32-bit units and erased in 2 kilobyte units. As I already said, the flash memory is divided into 16, 32 or 64 blocks of 2 kilobytes each depending on the total flash size. There are several security features available for flash: area protection, which enables rewriting for only selected blocks and disables programming for other blocks, but also protection against illicit tampering with or reading of data in flash memory, and others as well. Another designated area is the SRAM block, which is used for volatile data and is lost during a power cycle. The Dataflash block can also vary in size depending on the RA device, but in the case of the RA2E1 it is always 4 kilobytes in size. Dataflash can be programmed in 8-bit units and erased in 1 kilobyte units. In this block diagram we see that the flash is connected to the memory bus, but that the Dataflash is only connected to the internal peripheral bus. The Dataflash can be programmed and erased during operation without interfering with the normal flash process. Due to its finer granularity for both writing and erasing, and also the possibility to write on the fly during an application, Dataflash is also called virtual EEPROM. Many users wish to use the Dataflash on their MCUs as they would an EEPROM. The problem with this is that the Dataflash on RA MCUs does not have the same granularity or 1 byte write or 1 byte erase capability. Even if the RA MCU did offer this granularity, there would also be the issue of wear leveling and record management. To help solve these issues, the VEE project was created in the Flexible Software Package or FSP. And the VEE offers a lot of different features, such as listed here. In short, VEE stores data in a database-like format. Records are written much like a giant circular buffer, providing automatic wear leveling. An array is maintained in RAM, pointing to the most recent record of each type of data written for instant lookup and access. Data is formatted such that corrupted data from a reset during a write or erase operation is detectable during an open. All data management and error recovery is handled automatically. The user only has to perform read and writes. As already mentioned, Dataflash is a standard feature that is found on all RA devices. The only only the amount of data flash varies depending on the chosen RA device, ranging from 4 kilobytes to 64 kilobytes. Data can be any type of variable, but must be a multiple of 4 bytes, which is compatible with the minimum write size across all of the MCUs. Each unique type of data, for instance sensor data or communication data, is assigned an ID by the user, starting with 0 and incrementing from there. The data is stored along with its ID in a VEE flash database record. The most recent address of each record type is maintained in an array indexed by the ID. The highest ID is configured in properties and is used for the ERA declaration. All of this is maintained automatically by the driver. The record format is designed such that the data flash can be passed successfully even if a record is only partially written when a power loss or reset occurs. The validation field is a constant, hex BEAD, that denotes the entire record was completely written. Also easily identifies the end of the record and start of the next record in a flash memory dump. No checksum or CRC is created for records. Here we see an actual memory dump of the data flash. This is one record, and this is the first element of the record, which is the data size. Then the offset, which is internal to the driver and of no additional use for us, is to enable the driver to find the most recent record in an efficient way. Then the data elements here, which is 4. Then the ID code, and finally the validation code. Here we see the different records with different colors for clarity. So data flash is divided equally into areas called segments, a minimum of 2 of these, and the layout for a single segment is shown below. A segment consists of a header, which is 8 bytes, times the number of records, and optional reference data. If no reference data is present, then that area is also used for record storage. The optional reference data area is generally used for data that is only written once or maybe twice and not updated frequently, or at all. Typical data that would be suitable to write there would be a string containing the model number and a hardware calibration value programmed at the factory, or a MAC address for the Ethernet peripheral. When a segment has no more space for records or reference data, the most recent record of each ID type and reference data, if present, is copied into the next segment. Then the full segment is erased. This provides aware leveling over time. And here you see 4 segments in a row. Renesas provides an example project bundle for all of their RA evaluation boards. These demonstrate most, if not all, of the peripherals on the device. Renesas also provides a complete design package of all of its evaluation boards, including schematics and Gerber files. Example projects are available for all of the peripherals and are periodically updated and expanded. This is the RA2E1 microcontroller block diagram. The RA2E1 is developed on the 110 nanometer MF4 low power process and includes an ARM M23 CPU core with up to 48 MHz frequency operation. Operating from 1.6 to 5.5 volts and integrating a 1% accurate high-speed on-chip oscillator working from -4 or -40 to +105 degrees. The RA2E1 is offered with flash sizes from 32 up to 128 kilobytes and 16 bytes SRAM with parity. The RA2E1 has a lot of different peripherals, including communication and analog. It's also available in different packages such as QFN, LGA and also BGA. The RA2E1 has many interesting features, including low power consumption, a wide variety of peripherals, and lower BOM cost due to the integration of many normally external functions, including a high accuracy internal oscillator and of course Dataflash. The VEE or Dataflash example project for the EEPROM evaluation board demonstrates the basic functionalities of the VEE flash driver based on Renesas's FSP or flexible software package. However, I put an alternative example together that demonstrates a more real-world application. In this example, an ADC is periodically read when a key is pressed on the evaluation board. We can monitor this in the memory window of the E2 Studio IDE. When several readings are stored, we can erase the data flash by pressing a different key. This formats the data flash. Normally it would not be necessary to format in practice, as the Dataflash driver automatically implements wear leveling. So it's just as an example. Here you see the hardware configuration in this example. A variable resistor is connected to AN0 on P000. I will now demonstrate this alternative VEE example. Here we have the alternative VEE example project. I've loaded it into E2 Studio, and you can see that we're using FSP 3.7 and the target is the EEPROM board. If we have a look at the stacks page, you see that I've added the virtual EEPROM stack, the ADC stack, and two external IRQ stacks for the keys. If we have a look at the EEPROM properties, we see that we're using a max record ID of 16 and 2 segments. So with the RA2E1 we have 4 kilobytes of data flash divided into 2 segments, means that we are using two 2 kilobyte segments. The callback for the VEE is VEE underscore callback. The settings for the ADC are simply that we are using AN00, and the settings for the software key 1 is for IRQ3 on P004, and for the format switch, which is SW2, we're using IRQ7 on pin 015. Now if we have a look at the HAL entry where most of the code is placed, we see that we have a number of definitions, and in the HAL entry where the actual business happens, we initialize the interrupt, we start the ADC scan, we enable a while loop, and before the while loop is jumped into, we write a few sample records into the data flash as an example, and then during the while loop, if we press first the ADC is read and copied to a structure, and then if a software key is pressed or switch is pressed, press 1, then the record is loaded into Dataflash, and I put a breakpoint here so that we can have a look at the memory, and then if switch 2 is pressed, the Dataflash is formatted, and I've put a breakpoint there to have a look at the flash again. Callbacks for the VEE, callbacks for the interrupts for the keys, switch 1 and switch 2, and the target is down here on the bottom. Here we see the potentiometer, which we can vary, and the switch to store the data flash, and the switch to format the data flash. So without further ado, I'll compile the code and load it into the target. Here you see I've opened a window, a memory window at the start of the data flash memory. Now if I start the program, it will initiate the data flash driver, and you'll see that the data flash has been initialized and all set to FFF. If it hasn't been used before, it will be formatted and set to FFF. And the first address is indicated with BEAD. Now if I press run again, then the first example records will be written to flash. So press run, and now pause, and you'll see the first two records have been written. So first we wrote a record consisting of 4 elements: 1111, 3333, 5555 and 777, which indicate the ID temperature. So going through it, you see 8. The data size is 8 bytes, so 4 times 2 bytes. This is the offset, and then you have the data records 1, 3, 5 and 7. Then the record indicator, which is 1. ID temperature has the number 1. And then we go to the second record, which has a size of 2 bytes, an offset of 18, and the record itself is 1234, which we see here, which is pressure, and a packing byte, and then the ID indicator, which is 2 for ID pressure. We see that here. Now if I press run again, we'll go into the normal while loop, where the ADC is constantly updated. See that here. We'll set it to 1. And now if I press the right button, we'll hit a breakpoint in the write process, and you'll see that the first record has been written with a size of 2 bytes, offset of 24, a value of 2, which is the same as this hex 2 for the ADC data, a packing record, and then an ID record of 3. An ID record of 3 indicates it's the ADC values, and then a validation record BEAD. So if we repeat this, maybe change the value of the ADC, press the button, and once again we see the new record written, size of 2, offset, the value 613, which is, where's my window? There's my window again. 613, and then the ID number of 3. We can repeat this several times. Write data, start writing again, new data, change the value, FFF, write it. Now you see that the record value is FFF, which is the same as the variable, but you can also read the value in Dataflash with this line of code, value 1, which is also indicated up here, which is the same value as in your memory, which is the current record. And of course the variable can change still, but the loaded or stored record remains the same and can be used in your application, for instance for setting the temperature on the thermostat or other calibration data. Now of course, if you want to erase the data, which normally you wouldn't have to do, but just for example's sake, we run the program again, and then we press the number 2 switch to format the Dataflash. As you see here, we stop at the breakpoint, and we see that all of the pre-written values have been erased. And of course, we can start writing code again. This concludes this demonstration. The VEE driver APIs are fully documented in the FSP documentation. This can be downloaded from this URL. Implement these Dataflash features in your next application. The presentation and example project is included in the downloads. In closing, I would like to thank you for your attention, and if you have any questions or recommendations for future videos, don't hesitate to contact me on this address. Thank you for your time.